students. So we are discussing about real numbers, right? In our previous session we have studied about characteristic properties of supremum and infimum of real numbers, and also we have studied few more definitions. That is, we have studied about greatest number of a set bounded above and the smallest number of a set bounded below. So now today here in this session we are going to study about order completeness, or it is also called as completeness property of the set of real numbers. We are going to define about order completeness of real numbers. Let us know what does it states. The set of upper bounds of a non-empty set of real numbers, that is a non-empty set of real numbers, it is containing a set of upper bounds, okay, which is bounded above has the smallest number, is bounded above has the smallest number. See, among those set of upper bounds, it has a smallest number, what we call as supremum. That is what it can also be stated as. Equivalently, we may say that every non-empty set of real numbers which is bounded above admits add of a least upper bound. Means a set which is having a set of upper bounds, that is a real numbers of upper bounds, it has a least upper bound which we call as supremum. Or else we can say that the property of the set R of real numbers, the set R of real numbers, namely how that every non-empty subset of R which is bounded above admits of at least of least upper bound is referred to as ordered completeness or completeness property of real numbers. These are the definitions of what? Order completeness of real numbers. What it is actually stating is that if a non-empty set, if it is consisting of a set of all upper bounds, it has the smallest upper bound, at least one least upper bound, which we call as supremum in the set of real numbers. That is called as ordered completeness property or order completeness of the set of real numbers. Now let us study about one more property which is called as Archimedean property. That is also on the set of real numbers. That is Archimedean property on the set of real numbers. Okay. We are going to define it through a theorem here. What it is? Archimedean property of R, that is R in the sense real numbers. Archimedean property of R. Now what we are going to do is state and prove this Archimedean property of R. That is, now we shall state and prove this Archimedean property of R through one of the theorem. Then what does this theorem states? It states that if x and y are two given real numbers, if x and y are two given real numbers with x greater than 0, with x greater than 0, then there exists a natural number, then there exists a natural number, let us say n, such that such that n into x will be greater than y. So what we are doing now? We are stating and proving this Archimedean property on the set of real numbers, on the set of R. What does this theorem states? It states that if x and y are two given real numbers with x greater than 0, what is the condition they have given? They have given two real numbers. Which are those two real numbers? X and y are the two real numbers in such a way that x is greater than 0. So what they say? Then there exists a natural number n. Then if x and y are real numbers and x is greater than 0, then there exists one natural number n. How it is? It is in such a way that n into x will be greater than y. So to prove this, what we'll do is we are going to prove this theorem by the contradictory method. Contradictory method in the sense what? We are going to assume that there is no natural number n in such a way that it should be n into x will be greater than y. Like that, we are going to prove this theorem by contradictory method. At the end, we are going to prove that our assumption is wrong, and hence the theorem what it states is true. Let us start the proof. What we are going to say is, we assume the negation of the conclusion. Proof. We assume the negation of the conclusion what? To be true. Okay, to be established, and conclusion to be established and show. See, negation of the conclusion to be established in the sense by the contradictory method. The negation of this given statement, the opposite of this statement we are going to consider, and we are going to show that we arrive at a contradiction, and show that we arrive at a contradiction. What it is? We arrive at a contradiction. So we suppose that, now let us start proving it. Let us suppose that there exists no real number. Okay, let us start. Let us suppose that there exists no real number n such that n into x will be greater than y. See, we consider the contradictory, we consider the negation of the statement. What we have considered? We considered there exists no real number at all. What kind of real number is not there? The real number is not there in such a way that n into x, that is, let us suppose that there exists no real number or no natural number. Okay, no natural number n such that n into x is greater than y. Then what is going to happen? Greater than y. So that if it is not greater than y, then what is going to happen? N into x will be less than or equal to y for all n belongs to this set of natural numbers. So what is going to happen now? N into x is less than or equal to y for all n belongs to this set of natural numbers. If so, now what we are going to consider? We are going to consider a set A in such a way that consider a set consider a set A such that n into x. What we are considering? We are considering a set A which is equals to n into x such that n belongs to this set of natural numbers. Once we have considered this set, the set A is in accordance with our assumption. What we are going to say? The set A is in accordance with our assumption. What was our assumption? That is, we have no natural numbers, right? In accordance with our assumption, bounded above and y is an upper bound. With our assumption that it is bounded above and y is an upper bound. What we said? A set A is there which is satisfying the statement by having the upper bound y which is bounded. Y is an upper bound, okay, of this same set. So what is going to happen next? Then by the order completeness of R, just we have studied the definition, but then by the order completeness of R, set A admits of at least one upper bound, right? Then by order completeness of R, what the set A will be having? Set A has a least upper bound, right? What we are going to say? Set A has least upper bound, least upper bound. If set A is having the least upper bound, what we are going to do? Let alpha be this least upper bound. Let alpha be the least upper bound of what? Upper bound of set A. If alpha is the least upper bound of set A, how we are going to write it? We are going to write it as n into x. This will be less than or equal to alpha for all n belongs to this set of natural numbers. What we said? N into x is less than or equal to alpha. This implies what? This implies m plus 1 into x is less than or equal to alpha, where m also belongs to this natural numbers. That is, for all m belongs to this natural numbers. Again, how we can write it? We can write it as m into x plus x. This will be less than or equal to alpha. If it is less than or equal to alpha, what is going to happen next? We are going to say that this implies m into x is less than or equal to alpha minus x. That is plus x. I have shifted on this side. That is going to be minus x. M into x will be less than or equal to alpha minus x for all m belongs to this set of natural numbers. If m into x is less than or equal to alpha, then what is going to happen? Alpha minus x will be an upper bound. Therefore, alpha minus x is an upper bound. Okay. What we got now? Alpha minus x is an upper bound of what? Upper bound of this set A, right? Upper bound of A. So now what we got? We got alpha minus x as an upper bound of A. Since alpha minus x is obviously going to be less than alpha, right? Since alpha minus x that is less than alpha, we contradict the statement. What is going to happen? Since alpha minus x, this is obviously going to be what? This is going to be less than alpha. So what we obtained? We obtained the contradict that. We obtained to the contradiction that what we had considered alpha. Alpha is an upper bound we had considered, right? So this alpha is the least upper bound of A. That alpha is the least upper bound of A. If it is going to contradict, then what is going to happen? Alpha is the least upper bound of A. If so, thus the set A is not bounded above. Thus the set A is not bounded above. What we are going to say? Then the set A that will not be bounded above, and as such there exists a natural number, and as such there exists a natural number. What kind of natural number? We have considered n, no? There exists a natural number n such that what it is given? N into x, this is going to be greater than y. Hence, this is the proof of the theorem. Okay, let us glance once. What they have said, x and y are two real numbers, x is greater than 0. Then there is one natural number n. How it is? In such a way that n into x that is greater than y. So if it is like that, we have proved this theorem by contradiction method. What we have assumed? We suppose that there exists no natural number n such that n into x should be greater than y. So then what if it is not so? What it will happen? It happens that n into x will be less than or equal to y for all n belongs to this set of natural numbers. If so, what is going to happen? We are going to consider a set A. What kind of set it is? That set A, it is equals to n into x such that n belongs to this set of natural numbers. The set A is in accordance with our assumption that it is bounded above and y is an upper bound. Then according to this order completeness of R, set A should have at least one upper bound, right? At least has a least upper bound. And what we considered, let alpha be that least upper bound. If alpha is the least upper bound, then n into x that should be less than or equal to alpha. In place of n, it is a natural number, that is why m plus 1 into x, that is also going to be a natural number which is going to be less than or equal to alpha. If so, on simplification what I got m into x is less than or equal to alpha minus x. If it is less than or equal to alpha minus x, then alpha minus x should be the upper bound, right? So what happened? Alpha minus x is an upper bound of A. Since alpha minus x, what it is? It is obviously less than alpha. We obtained to the contradiction that alpha is the least upper bound of A. So we came to the contradiction that alpha is the least upper bound of A. Hence, what we got, the set A is bounded above, and how it is? It is in such a way that there exists natural number n such that n into x is greater than y. I hope you have understood this Archimedean property of real numbers. Let us move to the next topic. By considering we have no natural number to satisfy the condition of n into x greater than y, we came to the contradiction that our assumption is wrong and therefore there exists one natural number n. How? In such a way that at least one natural number n in such a way that n into x, that is going to be greater than y. Now let us move to the next thing. What they have given? Let us move to the Archimedean ordered field. We studied about complete order. We studied Archimedean property of R. Now we are going to study about Archimedean ordered field. What it is? Archimedean ordered field. So what it is? An ordered field, when we are going to say it as Archimedean, it has this Archimedean property of real numbers, as simple as that. That is, an ordered field, R is said to be Archimedean ordered field if it has what? If it has Archimedean property. If it has Archimedean property, that is Archimedean property. Very simple. When we, that is Archimedean ordered field. To satisfy this, it should first satisfy this Archimedean property. Let us consider one example. For example, what we are going to say is that the field R of set of all real numbers. The field R. What is R? Obviously the set of all real numbers, right? The set of all real numbers. The set of all real numbers is an Archimedean ordered field. Why? Because just now we proved that this set here R, it is going to satisfy this Archimedean property, right? That is why this field set of R, that is of real numbers, is an what? Archimedean ordered field. Let us go for one more theorem. Okay. What is the theorem given? The set n of natural numbers, the set n of natural numbers the set n of natural numbers is not bounded above, is not bounded above. See what we are supposed to prove? This set n of natural numbers, it is not bounded above. To prove this theorem, we have two methods. That is like we can say the method 1 and method 2. First, let us look over method 1. We shall prove the theorem and then go to the method 2. What we are going to do? Method 1. Let us consider, if possible, n is bounded above. Okay. Let, if possible, n is bounded above. Then according to the definition, what do you mean by bounded above? We mean that because why? See what happens if n is equals to 1, n will not be equal to an empty set, right? Then n became a non-empty set first of all. N is equals to 1, or we can say if 1 belongs to n, 1 is a natural number, right? If 1 belongs to n, so what is going to happen? N is not equal to 5. That is, since n is a non-empty and bounded above subset of R, since n is non-empty and bounded above subset of R. We know n is natural number. We know 1 is also natural. 1 belongs to n. It means what is going to happen? So n will not be an empty set. If n is non-empty and it is bounded above subset of R, so by ordered completeness property of real numbers, what we are going to say? So by ordered completeness property of real numbers, n should have what? N should have supremum, right? Real numbers, n must have what? N must have supremum. Yes or no? If it is bounded above, then by ordered completeness property, n must have supremum. Let us consider that as B. Okay, B, say, then what is going to happen? If it is having supremum, we are going to write it as, then n, this is going to be less than or equal to B, because what is B? B, it is the supremum for all n belongs to n. If so, like we have just proved the previous part, n plus 1 will be less than or equal to B. If n is less than or equal to B, what is going to happen? N plus 1, this will be less than or equal to B for all n belongs to n. Then what is going to happen? N will be less than or equal to B minus 1 for all n belongs to n. Just now while proving we had written it, right? N minus 1. Then what is going to happen? B minus 1 is going to be an, then B minus 1 is an upper bound. But what we know? We know that B minus 1, obviously it is going to be less than B. Yes or no? If so, like we have just proved, B minus 1 is an upper bound, then B minus 1 is less than B and supremum of n will be equal to B by our assumption. B minus 1 is what going to happen is an upper bound of n. Then B minus 1, which is less than B, and what is going to happen? Supremum of n will be equal to what? Supremum of n, that will be equal to B. By what? By our assumption. Yes or no? What we had said? B be the supremum, say then supremum of n became B. So we get an upper bound of n which is less than B. So now what we got? So we get an upper bound which is less than what? Which is less than B. But therefore this is going to be the contradiction, and hence what we got? We got to know that the set n of natural numbers, it is not having any, is not bounded above. We get contradicts the fact that B is the supremum of n. This contradicts the fact that B is an supremum of n. Therefore, what is going to happen? Therefore, n is not bounded above. Hence, n is not bounded above. What we considered? N be non-empty and let that be bounded above subset of R. If it is bounded above subset of R, then by this ordered completeness property of real numbers, n must have its supremum, right? Say let us consider B. Then we said that this n should be less than or equal to B. N is a set of natural numbers. It belongs to the set of natural numbers. If n is less than or equal to B, n plus 1 should be less than or equal to B. If so, what is going to happen? N that is going to be less than or equal to B minus 1 for all n belongs to this set of natural number. Then what is going to happen? Then B minus 1 will be an upper bound of n, right? We got B minus 1 is less than B and supremum of n will be equal to what? This supremum of n will be B by our assumption. Then what we got? Then we got an upper bound which is less than B. So this contradicts the fact that B is an supremum of n. Hence what we proved? We proved that this n it is not bounded above. We proved this by first method. Now let us look this proof by the second method. Okay, the same theorem we have one more proof. Let us start proving that by this Archimedean property. Okay. Second method, by the Archimedean property of real numbers, we are going to prove that. That is, by the Archimedean property of real numbers. What we have? Archimedean property of real numbers. For each positive real number x, for each positive real number x, and for this n belongs to n, there exists x greater than 0, right? There exists x greater than 0 such that, how it was? N into x greater than y. This was the Archimedean property, right? Such that, or else we can write n, this is greater than x. N greater than x. For each positive real number, that is, there exists x greater than 0 in the sense this is a positive real number, such that this n is going to be greater than x. See what happens? For n greater than, for positive real number x and for all n belongs to n, what we are going to get? We are going to get then this n is greater than x. If so, what is going to happen by this? Hence, there exists no positive real number x in row real number x such that then there exists no positive real number x such that it should not be less than or equal to, no, right? Hence, there exists no positive real number x. In what way? Such that this n is less than or equal to x for all n belongs to this set of natural numbers. If so, what is going to happen? If there exists no positive real number x, which is where n is less than or equal to x, then what is going to happen? No positive real number is an, this implies what? This implies no positive real number, no positive real number is an upper bound of n. Hence this is the proof. Hence the proof. Very simple thing. What we studied? What we considered? Second method, we proved this by Archimedean property of real numbers. What it stated? It stated that for each positive real number x and for n belongs to n, then what is going to happen? Then n will be greater than x. Then if n is greater than x, what is going to happen? There exists no positive real number x such a way that this n is less than or equal to s. If this is not possible, if this does not exist, then obviously n will not be having any upper bound. There will be no positive real number which is an upper bound of n. Hence we proved that the set n of natural numbers is not bounded above. Let us move to the another theorem, the denseness property. Okay, denseness, where we are going to say that between two real numbers there exists a rational number. The denseness property of the set of real numbers. The denseness property of the set of real numbers. Again, let us study this with the theorem. The theorem itself is called as the denseness theorem. Okay, what the theorem is called? The density theorem. The density theorem. Let us know what it states. It states that between any two distinct real numbers, between any two distinct real numbers, what is going to happen? There always lies a rational number. There always lies a rational number. See what they have given. What is that density theorem? What does it state? It states that in between any two distinct real numbers, might be any two different real numbers, there always lies a rational number. Let us prove this. Let us consider x and y be two distinct real numbers. Proof: let x and y be two distinct real numbers, and let us consider x to be less than y and x is less than y. Then there exists a natural, then there exists a rational number. A rational number. How this natural number should be? Rational number are such that, see, this rational number r it should be in between these two distinct real numbers. Yes or no? Therefore, this R, it is greater than 0, sorry, greater than x, and it should be less than y. There exists a natural number, rational number R, such that R that is greater than x and less than y. So, we firstly suppose that x is greater than 0. We are first going to consider. We firstly suppose that x is greater than 0. What happens if x is greater than 0? It means also what is going to happen? We have considered x greater than 0 and also y greater than x. Right? X is greater than 0 and y is greater than x. This implies what? This implies x minus y. This is going to be greater than, sorry, this implies y minus x. This will be greater than 0. So, what is going to happen now? Y minus x is going to be greater than 0. Now, by the Archimedean property of R, there exists a natural number Q. Now, what is going to happen? By Archimedean property of R, there exists a real number Q such that, how it is going to happen? Such that Q into y minus x, that is going to be greater than Q into y minus x. This is going to be greater than 1. What we considered? We considered that by Archimedean property, Q into y minus x, that is greater than 1. This implies what? This implies this 1 minus q, it is going to be less than y minus x, right? 1 my q, that is going to be less than y minus x. Again, by the Archimedean property of R, what is going to happen? There exists a natural number n. Again, by Archimedean property, there exists a natural number. There exists a natural number n such that this n is greater than q into x. Again, by this Archimedean property itself, what we got? We got a natural number n which is in such a way that n is greater than q into x. Now, what we are going to do? Let p be the smallest such natural number, so that p is the smallest natural number such that, now what we are going to consider? Like that, by considering like this by Archimedean properties, we are going to consider p be one of the natural number of n, so that let p be the smallest such number of n. So, what is going to happen? So, that p is the smallest natural number. So, that p is the smallest natural number. In what way? Such that this P, how it should be? Such that this P that should be, that is such that Q into X should be less than P. What we were doing actually is considering like this Archimedean properties, we were showing that this N is greater than QS. Continuously considering like this, what we said is P be the smallest number of this like this, then what is going to be happened? This Q into X, that is going to be what? That is going to be less than P. Then if P is equals to 1, so what is going to happen? So that P minus 1 is equals to 0. If P is equals to 1, so that what is going to happen? P minus 1, this is going to be equal to 0, right? If P is equals to 1, P minus 1 will be equal to 0. We have what? We have P minus 1 which is equals to 0. This is going to be less than what? That is going to be less than Q into X. This is going to be less than what? 1 minus P. What is going to happen? P minus 1 which is equals to 0. This is less than Q into X. This is going to be less than what? It is going to be less than 1. So it is going to be less than 1 which is equals to P, because we have considered P is equals to 1. This is going to be less than 1 which is equals to P. If so, what we are going to get? We are going to get is, this implies P minus 1. This is going to be less than what? P minus 1 is going to be less than Q into X. This is going to be less than P. See, 1 that is equals to P, because we have considered P is equals to 1. So we got P minus 1 less than Q into X, which is less than P. If so, if P is greater than or equal to 2, so that P minus 1 is a natural number. Again, if P is greater than or equal to 2, what is going to happen if P is greater than or equal to 2? So that P minus 1 is again a natural number. Yes or no? So that P minus 1 is a natural number. If P minus 1 here now is a natural number, we have by the definition of P, we have by definition of, what is the definition of P? What we have by the definition of P, that P minus 1 is less than Q. Yes or no? P minus 1, that is going to be less than Q into X. We here have, see, P minus 1, that is going to be less than Q into X. Now what is going to happen? Qx then Q into X, it is less than P. We have here already Q into X, that is less than P. This implies what? This will be equal to what? We are just going to simplify. That is P minus 1 plus 1, that is, this will be equal to P minus 1 plus 1, nothing but we are going to get P itself, that is going to be less than Qx, that is going to be less than Qx. This is going to be what? Q into, how we can write X? See, we can write X as Y minus X, which is equals to what? Q into Y. This is going to be equal to Q into Y. This implies what? This implies this Qx, it is going to be less than Q, less than or equal to Qy, less than Q. less than P, because of course less than P, which is less than Q into Y. This implies what? This X is less than P by Q and this is going to be less than Y, where P by Q is going to be obviously a rational number. We now consider the case when X is less than or equal to 0. We now consider when this X is less than or equal to 0. We proved this when X is greater than 0. What happens if X is less than or equal to 0? Again, by this Archimedean property R, there exists a natural number K such that, see, I am not going to write the entire part. By this Archimedean property of R, there exists one number K. What kind of number K we have? We have K such a way that we have a number K. How? Such that K is equals to K into 1, which is greater than X. This is by the Archimedean property of R. This implies what? This implies K plus X is greater than 0. Obviously, K into 1 is K itself. K plus 1, that is going to be what? This is K into 1 is going to be greater than minus X. Then K plus X is going to be greater than 0. There exists therefore a rational number. Say yes. Therefore, there exists a rational number. Let us consider it as yes, okay? Yes. Say yes. How it is? In such a way that this K plus X, how this K plus X should be? That should be less than yes. And how it should be further? This should be less than K plus Y. Then what is going to happen? This X, that is going to be less than S minus K, which is going to be less than Y. Again, what we got here? This S minus K is a, hence S minus K is a rational number. This is the proof of the theorem. We mean to just show that for any two different real numbers, then in between we have a rational number. For that, what we considered, X and Y, let them be two distinct real numbers. The condition that X should be less than Y. Then what we said, then there exists a rational number R. How this rational number is? This R, it is greater than X and less than Y. So, to prove this, first we need to consider X greater than 0 and secondly we need to consider X less than or equal to 0. For X greater than 0, what we did? We said X is greater than 0 and Y is greater than X. If so, what we are going to get? This Y minus X, obviously this is going to be greater than 0. If Y minus X is greater than 0, what we did? We applied this Archimedean property of R, that there exists a real number Q. How it is? In such a way that Q into Y minus X, that is greater than 1. If so, what it implies? It implies 1 minus Q, that is less than Y minus X. Again, what we did by this Archimedean property, we said there exists a natural number. How it is? This N, it is greater than Q into X. Like this, what we said, like that, P be the smallest of this N, then P is going to be the smallest natural number. If P is the smallest natural number, then Q into X is going to be less than P. What happens if P is equals to 1? Obviously, P minus 1 will be equal to 0. Then we have P minus 1, 0, which is less than q into x, which is less than 1, which is equals to p. Then we said that p minus 1 is less than qx, which is less than p. What happens if p is greater than or equal to 2? We said that p minus 1 is a natural number. Then what we had by definition? P minus 1, that would be less than qx. If so, what we said? Qx, if it is less than p, it implies p minus 1 plus 1, nothing but p, less than qx. This is less than q into y minus x. Y minus x we considered as qy. Then what we got? Qx, it is less than p, which is less than qy. So what we got? X, this p by q is greater than x and less than y, and we know that p by q is a rational number. This is when x is greater than 0. What happens if x is less than or equal to 0? We said again by the Archimedean property of R, there exists one number k. How? In such a way that this is equals to k into 1. It is greater than minus x. Why we have considered minus x? Because here x is less than or equal to 0. So what happened? X, so k plus x, this will be equal greater than 0. Then there exists a rational number yes. How? K plus x, it is going to be less than yes, and s is less than k plus y. Then what we got? We got s minus k, which is again a rational number. This is like this. In between any two distinct real numbers, there exists what? There exists a rational number. I hope you all have understood this, the density theorem. Now let us move to one more theorem. The next theorem is that if x and y are two real numbers, what it is? If x and y are two real numbers, if x comma y are two real numbers with x less than y, then there exists an irrational number, then there exists an irrational number I such that I is greater than x and less than y. So students, just now we had proved the same theorem for rational numbers, right? Now we are going to prove this theorem for irrational number. That is, if x and y, if they are two distinct real numbers, with the condition here is what? That here x is less than y, then there exists an irrational number I. How this irrational number is? It is greater than x and less than y. Let us start proving it. We have to show that there exists an irrational number, right? How it should be irrational number between any two given real numbers. We have to show that there exists an irrational number between any two real numbers. Now here we are going to consider two cases, that is case 1 and case 2. Here case 1, x be irrational, and case 2, what happens if x is a rational number. We are going to prove this theorem by two cases. Case 1, x is irrational number, and case 2 if x is a rational number. Let us start proving with case 1. Let x be an irrational number. Case 1, let x be an irrational number. What is going to happen if we consider x as an irrational number? See, we know that there exists a rational number r. We already know. Just now we have proved. We know that there exists a rational number. Just now in the previous theorem we have proved, right? A rational number r such that what had happened? This r, it was greater than x and less than y. This was the thing we have just now proved. If so, what we are going to do? Consider a number. Now, consider a number x plus r by 2, which obviously when we say is going to be an what? Be an irrational number, which may be easily shown as irrational number, which may be easily shown as what? Easily shown as irrational number. And again, what we are going to consider? This x plus r divided by 2, that should be, if it is going to be an irrational number, it is very easy thing to tell. What it is very easy to tell? We may also then, if it is an irrational number, we may show that, what we can show? We can say that this x plus r by 2, it is greater than x and it is less than y. So what we said? X plus r by 2, that is greater than x and less than y. Hence what we proved? We proved that x plus r by 2, what it is an irrational number. Thus, x plus r by 2 is an irrational number between what? Irrational number between x and y. So now we proved for x if it is irrational. What about case 2? We are going to consider if x is an rational number. If x is a rational number. See, what we are going to do here is, we all very well know that root 2 is an irrational number, right? We are going to consider this simple fact and prove this case too if x is a rational number. We shall make use of the known fact. Which is the known fact? We shall make use of the known fact that root 2 is irrational. We all know it very well, right? Root 2 is irrational. Using this, we are going to prove this case too. That is, let r be a rational number between x and y. Let r be a rational number between x and y. What we considered? R as a rational number between x and y. What it is? If it is a rational number between x and y, it is obvious that, so that this r, it is greater than x and less than y, right? So next what is going to happen? So that r is greater than x and less than y. Now what we are going to do is, r as x minus r, see, as x minus r, it is going to be less than what? It is going to be less than 0. Why? Because r is greater than x. Or let us see, as r minus x is greater than 0, there exists a natural number n, such that n into r minus x, what is going to happen? Such that n into r minus x, here we had considered what? This is going to be greater than root 2. n into r minus x, that is going to be greater than root 2. It implies what? It implies root 2 divided by n. It implies what? Root 2 divided by n, that is going to be less than r minus x. Root 2 divided by n, that is going to be what? Less than r minus x. Let what we say? Let I is equals to x plus, see what we are doing is I is equals to x plus root 2n, so that if I is equals to x plus root 2n, then what is going to happen? So that this I is less than r, then what we are going to get? If r is a rational number, then we are going to get x less than I less than r, which is going to be less than y. Then what we got? We got I, which is greater than x and less than y, which is I is irrational number. So here I is an irrational number. That is why we proved that there exist irrational numbers between two distinct what? Between two real numbers. We showed that what? We considered case 1 where x is an irrational number. If irrational, then what we said? For rational numbers, we have r greater than x and less than y. We considered a number x plus r by 2, which easily can be shown that it is irrational. So what we did? X plus r by 2, that is greater than x and less than y. We proved that that is an irrational number between x and y. What happens if x is a rational number? We proved this case 2 by a very well known fact, which is root 2 is an irrational number. Then we considered if r is a rational number between x and y, this r is greater than x and less than y. So what happens here? This r minus x, it is going to be greater than 0. Then what we said? Then there exists a natural number n. How this natural number should be? N into r minus x, this should be greater than root 2. Then what is going to happen? Root 2 by n, that is going to be less than r minus x. But what we considered? Considered I is equals to x plus root 2 n. That right? What we consider? I is equals to x plus root 2 n, so that this I is less than r. So again by this what we got? We got x is less than I, less than r and less than y. Hence we proved that this I, where I is an irrational number, that is greater than x and less than y. Hence the proof of the theorem that there exists an irrational number I such that I is greater than x and less than y. So students, I hope you all have followed the today's topic. Stay safe, keep studying, and thank you.